the atmospheric concentrations of all species increased from the pre-industry times to the present. And that drives the climate change, depending on their optical properties. And both positive and the negative effects appeared. But the one thing to note is that the aerosols has increased, but they're overturned already, and that will affect the future climate. The warming or cooling contributions per chemical species can be shown as their time evolution to provide more information. For example, occasional volcano eruptions shown in green cool the temperature and were the dominant features in the 19th century. However, these individual events lasted only for less than 10 years. After 1950, the dominant feature became continued rise due to CO2, methane, and ozone increases, which were partly compensated by the increases in the tropospheric aerosols, as seen in the last slide. Here, by identifying the large contributions of CO2, the D.1 statement of the summary for policymakers occurred as limiting CO2 emissions or reaching net zero CO2 emissions are required to limit the global warming. But here, another important point is that the cooling due to the tropospheric aerosol has peaked out, and now it changes to upward shift, namely the relative warming from now. This is due to declining aerosol pollution, as seen before. The scenarios intentionally maintaining the current level of tropospheric aerosols may continue to cool the Earth system, but are not recommended in terms of health and air quality. This is not my personal interpretation, but what IPCC report really said. So we have double pain from aerosol warming and CO2 warming. A possible remedy to this inevitable warming would be from rapid reduction of methane emissions. Thus, the second part of the statement says, strong, rapid, and sustained reductions in methane emissions would also limit the warming effect resulting from declining aerosol pollution. So this is the main storyline that I will highlight in the following slides. Here, the bars show warming and cooling contributions from species after 10 and 100 years of a hypothetical single year of emissions. For the 100 years case in the bottom, the CO2 in yellow is dominant, and is surely the most important target of mitigation. But the methane contribution becomes relatively larger for the time scale of 10 years near its atmospheric residence time. And the breakdown of the contribution to emission sectors and to the emission regions suggests that CO2 from energy production and industry from East Asia, North America, and Europe, or methane from fossil fuel production, agriculture, and waste management from East Asia and South Asia as well, sometimes from Latin America, are dominant. Future temperature projections are the major output of the IPCC report and are often displayed with 5 core SSB scenarios, emission scenarios for CO2. The scenarios have their names such as SSB 1-1.9, but here we call them simply very low, low, intermediate, high, and very high scenarios, similar to the text in SPM. For example, in all scenarios, the temperature rise reaches 1.5 degrees Celsius within 20 years, but the differences become larger later. The Paris Agreement aims 1.5 or 2.0 degrees Celsius, and they correspond to very low and low scenarios where net CO2 emissions become zero or negative around 2055 or 2075. The intermediate scenario is set at the path we are now on. And the high and very high scenarios are based on more emissions in the regional rivalry or the fossil fuel intensive world. But the scenarios support not only CO2 emissions, but also all relevant SLCF species, including methane, black carbon, OC, SO2, NOx, CO, NMVOC, and ammonia, and HFCs. And they were used for the future projection and concentrations and impact. The basic feature might be similar to CO2, namely the low emissions in low emission scenarios, as generally controls pretty much similarly affect both CO2 and SLCFs. Earlier peaks for SLCFs, particularly for SO2 and NOx, than that for CO2 are to be highlighted. SO2 and NOx already peaked out, as removal technology application is easier than CO2. As they are major aerosol precursors, the aerosol pollution reduction has already started. From now, such trend will continue and the temperature rise is inevitable. In reference to 2019, the temperature rise due only to aerosol change will be at maximum 0.4 degrees Celsius in the case of very clean, very low emission scenario. And this warming effect could be limited by methane and ozone when methane emission reduction becomes successful, though not very easy now. As the lifetime of methane is about 10 years, its concentration will decrease pretty fast as the emission decreases in the low scenarios. And the cooling from 2019 is expected in the range of 0.1 or 0.2 degrees Celsius. When NOx is reduced, the tropospheric ozone formed by photochemistry of NOx and methane will also be reduced. And therefore, the additional cooling is expected due to the ozone decrease. So together, the cooling will be in the range of 0.3 or 0.4 degrees Celsius by 2100, compensating the warming due to the declining aerosols. But this is only when the successful emission reduction for methane is achieved. So here's a net total effect from SLCFs, including aerosols, methane, ozone, and HFCs is depicted. All scenarios led to warming toward the 2100, but the range is wide, ranging from 0.1 to 0.6 degrees Celsius. As we saw at the beginning, when we aim limiting to within 1.5 degrees from the pre-industrial times, the allowed temperature rise from now on is only 0.4 degrees. Depending on scenarios, that allowance is easily filled by the change in SLCFs only, not by CO2. Therefore, controls of SLCFs are also important as well as that for CO2. This situation is demonstrated in another way. The global surface temperature increase since pre-industrial times is said proportional to the cumulative CO2 emissions since 1850. This is a concept of the carbon budget. The temperature rise in the past by 1.1 degrees corresponds to the equivalent total CO2 emissions so far. To the target of 1.5 degrees Celsius, the margin of 0.4 degrees might correspond to the remaining carbon budget of this width of about 800 gigatons CO2, but it is not in reality due to the presence of non-CO2 or SLCFs. So we need to allocate a part of the temperature margin to SLCFs to by about 0.2 degrees, as we saw in the last slide, even in the smallest case. In the remaining carbon budget, the allowed CO2 emission from now must be diminished to 500 gigatons CO2. Considering the recent annual emission of CO2 of 43 gigatons CO2, this corresponds to only 12 years of emission. This is why urgent emission reductions are seriously discussed. The partitioning is also affected by the process representation uncertainties in the model, such as the potential feedback from more frequent forest fire occurrence. Therefore, the behavior of SLCF species determines the maximum CO2 amount allowed to emit, and thus they are important to study. The warming from reduced aerosol pollution mentioned so far was already demonstrated during the COVID-19 lockdown period. Limited human activity in 2020 resulted in about 5.4% reduction in the CO2 emissions and must have resulted in some cooling in comparison to the case without the reduction. However, the aerosols were similarly reduced by the reduced human activities, as depicted by the green color here, showing the AOD reduction over Asia particularly. The media also showed blue sky is returned over in India, where otherwise the hazy condition was typical. Such reduced aerosols increased insolation to the ground and must have induced warming. The two counteracting effects, heating by reduced aerosols and cooling by reduced CO2, must have compensated each other, and the temperature change from simulation models remained almost unchanged. So far, the major storyline from AL6 was presented, and now we move on to the second part, how aerosols as pollutants, particularly those in Asia, are mentioned in the IPCC report. They are presented with 3 questions and answers in my talk. The first question is about as if the IPCC report describes climate effect only and ignore air quality health effect aspects. The answer is surely no. Air quality is rather concerned with top priority rather than climate from the standpoint of sustainability. The left panel from Chapter 6 describes the current PM2.5 levels estimated in the model at the surface for regions including Eastern and Southern Asia. There, the contribution from energy, industry, and residential sectors are important, as shown by these colors. In the right-hand side, the future projections are shown. And in the blue colored low emission scenario like this, the PM2.5 in Eastern Asia is reduced from 17 to 9 or 7 microgram per cubic meter in 2040 and 2100, demonstrating the benefit of improved air quality at the cost of future warming. And though the lowered level do not necessarily reach the recently tightened WHO guideline levels of 5 microgram per cubic meter, that this reduction is substantial. A related SPM statement could be interpreted as the air quality improvement is a good sign for successful mitigation for climate. Low or very low scenarios in blue here result in the reduction in both ozone and PM2.5 concentration at surface in 2040. The discernible differences in trends of global surface temperature would begin to emerge within 20 years, as shown in gray bars in the left, as net total effects from GHGs and SLCFs, shown here. While the contribution of SLCF is positive in net total due to declining aerosols, the total temperature effect is less than those in the high emission scenarios. The second question is about Asia, was Asian information supplied enough to AL6? I hope to say yes, but could be improved next time. The importance of Asia in terms of SLCFs is clear, as the regional emission fractions of all of the SLCFs are more than half, as shown here, like this, ranging from Southern Asia to the East Asia in these colors, from orange to the red. And they are rapidly changing, so the tracking the emission is quite important. And also recently, satellite measurement over Asia is also providing a lot of information. And with some delay, for example, the eastern and northwestern China have experienced NO2 peaks as an aerosol precursors in 2011 and 2013, and decreases have already started. The spatial variability of PM2.5 composition is also depicted in a figure from chapter 6. The density of measurements over Asia was not that high in comparison to the US and Europe, but Asian observational network data such as ENET or the Spoutan for several selected cities and the CARE China network are also used in this map. Other 9 original studies were also used to increase the coverage, as shown here. For Eastern Asia, the high OC and black carbon concentrations are featured, but still the coverage over the Southern Asia, for example, is poor and needs to be improved in the future report. Data gathering activities from Asian research community in the audience at the right timing before assessment report will help the future IPCC authors and will be strategically meaningful. The trends of SO2 and sulfate for different periods were summarized in table 6.5. Here, the reduction in Asia has not been well captured to the time of 2015, like this, shown red. And Ars et al. Was from Aerocom, summarizing both model simulations and observations as benchmarks. Here, the ENET data were mainly incorporated, though the network name is not instantaneously visible in this table. And for black carbon and organic aerosols OA and total carbon TC, even fewer, smaller number of data were cited. For black carbon from Asia, only 2 data, as shown in orange, with long-term record at background sites were cited, describing faster decreases about 5% per year, influenced by emission change from China and India. OA and TC are all from United States and Europe. And then the more long-term studies in Asia are to be appreciated. So one of the studies in Asia were from our study at Fukui Island, Western Japan, sampling Chinese emission change outflow within the winter monsoon system. And some more details than cited are summarized here in the 2 slides. The long-term observations till 2019 showed a significant decreasing trend in the black carbon concentrations, minus 5.8% per year in average, and the concentration levels nearly halved during the last decade. Although a significant emission reduction in the upwind region is implied, here a caution was exercised as a concentration trend could be impacted by meteorological change. So in this study, the meteorological factors were carefully removed to extract the emission trend. First, analysis on air mass only air masses originated from China was made. Secondly, data influenced by wet deposition were discarded. The dilution diffusion term was further corrected using the WRF-CMAC chemical transport model simulations, which showed a superior performance in predicting the timings of the arrival of the polluted air masses and their relative magnitude. So here in the model, the emission rates were artificially fixed to a certain reference value, and rather the emission scaling or correction factors were estimated as a ratios with the ratios of observation to model concentration for each year, which could bring the model levels into agreement with observations, assuming a linear response. And the trend scaling factor was analyzed like this. And then we finally estimated a 4.6% year of decreasing trend for the national total emissions of black carbon. The absolute emission rate could be also be calculated back by multiplying the estimated emission scaling factor to the reference emission rate. Here's the total emission, and the change estimated from this study is shown by red here in comparison to other bottom-up type of emission estimated emissions. Clearly, the total amount is around 1 teragram recently, and not 2 teragrams as shown, as indicated, as estimated in bottom-up estimates. The positive trend from CETS was not supported from this study. Alternatively, the estimates from decreasing trends reflecting governmental clean air actions for reducing PM2.5 was supported. With this, the CDS for CMIP6 was updated afterward with downward shift, so not in time for the AL6 assessment. Even though reduced, the 1 teragram black carbon emission is substantial and is about 30 times larger than the emission from Japan, or 3 times on the per capita basis. And thus, the major emitting sector identification will still be needed to pinpoint the further mitigation strategy. Using the black carbon data during the COVID-19 affecting period, we identified at Fukui Island that the dominant sector as the residential sector. Our analysis showed only small 80% emission decreases was present with the Chinese black carbon during the lockdown. And we interpreted this as a large fraction was continuously emitted even under the lockdown period, particularly from the residential sector regarding heating and cooking. Among the variety of the bottom-up emission inventories, the Make 1.3 or Eclipse version 6.6b was well supported in terms of the dominance of the residential sector as shown in orange color here. And from a marginal abatement cost analysis, MAC analysis, based on emission details from Eclipse version 6b, we find the mitigation of the dominant residential black carbon emission from China is achievable at relatively low cost. This analysis overall pinpointed the possible mitigation option in the near future. This slide covers a bit different aspect, but again related to the visibility or coverage of Asian aerosol studies in the AR6 Working Group 1 report. During the report development, the first and second order draft FOD and SOD were open to experts, and the comments and revisions were made. Here, my role as a review editor was to watch this process. Upon encouragement from me and other 2 review editors, the number of comments from Asian and African scientists increased, but was not very high. So this may be the point of future improvement to increase visibility of Asian research. Move on to the question number 3. So now we are 100% sure about the climate change driver as human. Then does this mean that the climate effects from aerosols clouds are fully understood? The answer is no, surely not. The unequivocal statement at the beginning came from a narrowed AL6 climate sensitivity depicted here in the left panel as a likely range from 2.5 to 4 degrees Celsius in comparison to the previous estimates, wider estimates in AL5 or the areas. The climate sensitivity is a temperature increase against hypothetical doubled CO2 concentrations, including the cloud system. So this was narrowed not because process-based understanding progressed, but because other evidence became reliable about the real historical temperature response to the past perturbations. And in the right-hand panel, when based on the processes, large uncertainty still remains regarding the effective radiative forcing from aerosols, particularly with the aerosol cloud interactions. And which part of aerosol understanding was rated with low confidence is summarized here to perhaps tell which research is needed in the future. 3 topics are raised here. One is on SOA, secondary organic aerosols formation. And AL6 assessed that SOA production rates varied by a factor of 10 depending on studies. Limitations is in the process level understanding of formation, aging, and removal are highlighted. The second is about the brown carbon, a class of organic carbon but absorbs UV short visible radiation may contribute to the warming side. The brown carbon can be present as much as 20% of organic aerosols or as much as black carbon in one study shows. The third is about the INP, the ice nucleated particles. Previously, the black carbon was regarded as a class of INP, but recently a counter evidence has occurred from a laboratory study that is cited in the AL6. So more evidence from the field would be necessary to be conclusive. So Asia and downwind area might be perhaps the area having the regional advantage to study all of them. So far, we discussed the roles of SLCFs in the global scale climate system and associated Asian aerosol studies and the future requirement. In the last part of my talk, I hope to mention their impact on the Arctic, where the warming is occurring in a much faster pace. The Arctic Council Arctic Monitoring and Assessment Program, AMAP, has published a report, and this summary for policymakers in 2021. The diagram in the right-hand side from the report shows the temperature rise during the 60 years around now in the past and the future, and now it's about the temperature rise is so huge, and it's as much as 3 degrees. The global CO2 increase and the sulfate reduction again hit the Arctic, similarly to the global case shown here in the gray and the yellow shows them. But the difference is that a part of this can be counterbalanced by the black carbon reduction when achieved, as shown by green. The Arctic version of species contribution to effective radiative forcing is shown here. And this is from Oshima et al. Using Japan Meteorological Research Institute model participating in both CMIP6 and for IPCC and also the AMAP model comparison. Again, the largest ERF, effective radiative forcing, is from CO2 as much as 1.47 watts per square meter. But the black carbon is secondarily important. In total, 0.61 watt per square meter. When the quantity is subdivided into processes, the surface albedo effect was as much as 1.08 watt per square meter. The ALERT is a Canadian high-latitude monitoring station for long-term observations. There, the atmospheric black carbon concentration decreased till 2000, the year of 2000, due mainly to the emission reduction in the US and Europe, but has stagnated in the recent decade, and more studies are necessary for this aspect. The NIS group from Japan and us from JAMSTEC jointly participated in the Arctic-related research project, and the PACES, the IGAC and IAST's joint research activity on the Arctic study. Using an atmospheric chemistry modeling system tuned to observations, the basic contribution of the globally distributed black carbon sources over the Arctic region was depicted. At the 5-kilometer altitude or in the free troposphere, and for the full atmospheric burden, the contribution from East Asian anthropogenic was dominant as shown by red. While at the surface and for the deposited black carbon amount, the contribution from Russian anthropogenic sources are dominant as shown by orange for the 5 years of the average. The contribution from boreal forest fires showing green and brown are important in limited months in summer in the recent 5 years, but may rise in the future as the Earth system model suggests that the black carbon emission from boreal fires may increase by a factor of 6 to 10 by the 2100 year. JAMSTEC as Marine Research Organization put our observational efforts to ship-based survey for long and atmospheric observations of black carbon, other aerosols, ozone and CO and MAXDOS are regularly made for about 10 years. Our black carbon observations by the SP2 instrument with a very high sensitivity enabled measurements down to less than 0.001 microgram per cubic meter or the 1 nanogram per cubic meter, and were used for the model evaluation participating in the AMAP assessment report. The red dots in the right panels are from our observations with low levels. Several models with yellow resulted in a significant overestimation by an order of magnitude in that low black carbon concentration range, while other models are almost successfully reproducing our model simulation through down to the low concentration levels. By studying the processes employed in the individual models, we hope to identify the processes responsible for the reproducibility, and the way forward, how to revise the models toward better agreement with observations. Emission quantification and their change detection are central to the mitigation efforts. It has been decided that IPCC Task Force on Inventory, TFI, will lead the methodological development toward national SLCF emission inventory reporting in the AR7 cycle to be mandated, in addition to GHGs in the future. And the Arctic Council now mandates the national reporting of the black carbon and methane emissions from 8 member countries facing directly to the Arctic Ocean, as well as the observer countries in that framework, including China, India, and Japan. Basic collection of information such as emission factors and relevant activities for each SLCFs, considering practices and their change that may be rapid in individual countries or regions will be required. So roles of scientists are now expanded to include reporting those societally relevant information, increasing their accuracy and supporting policy with scientific evidence. So now to summarize, I delivered the major storyline of the IPCC L6 Working Group 1 report about GHGs and SLCFs, particularly focusing on the declining aerosols in the future will strengthen the future warming. And how the Asian aerosol studies were assessed in the report was summarized, and potential more association of the Asian aerosol scientists and the results in the future assessment report are discussed. And also, I suggest some new directions beyond the AL6, particularly on the process studies of the brown carbon, SOA, NPs, and the studies on the related SLCF inventory, emission inventory that IPCC will support, and also the studies on related Arctic climate and environmental changes are required. That's all from me. Thank you very much.
All right, thank you very much. It was a very nice talk, putting together everything, very important aspects from IPCC, and also highlighting Asian aerosols, which fits with the conference theme. So while Hugo is standing by to answer to any questions, any easy questions or any difficult questions, if there's any. And I think we have a few minutes for the question discussion time. And I believe, I think after the three speakers, we have some discussion session, but we can take questions if any, I guess. Or is that correct process to do?
Any question from the on-site? Yeah, Charles.
Ah, Charles, okay, go ahead.
Yeah, so you go. Thank you.
Thank you.
Very nice talk. And actually, I have a very direct and I'm not sure it's simple or not simple question. Is that in the report, a very important point is that among your projection, you expect a decline in ozone contribution to warming. Okay, so that means you expect a decline in the ozone production in troposphere. But actually, during the last 10 or 20 years, records of observation, we did not see a significant reduction in ozone, despite of the air quality improvements in many locations around the world. So we would like to make a comment to the disagreement in modeling output and the observation upon ozone, and what you expect to the further trend in ozone production and the impact to regional climate. Yeah.
Yeah, thank you very much for the important question about the ozone future. And with one slide, I presented in such a way that with only when the methane emission is reduced, the ozone may come down. Otherwise, the ozone is developing. And right now, Charles is right, that in Taiwan, in Japan, in China, particularly, the surface ozone is rising. And the scientists are still wondering what would be the exact cause for that, particularly for the chemistry, it's nonlinear chemistry, or some heterogeneous reactions might participate in that, or there's some transportation change or something like that, stagnation, including stagnation. But chemically, it should rise without any strong reduction in the precursor emissions like NOx and VOC, including VOC, CO, methane. But still, with the reduction in NOx and methane, there is the trick in the nonlinear chemistry of tropospheric ozone. So it's not very easy to reduce the ozone levels. So then, but with the significant reduction in methane, for example, particularly for 30% reduction in 10 years, as such, the methane concentration will reduced to the very low levels that people might have experienced in several tens of years ancient time, around 70s or something like that. Then with that level, the tropospheric ozone is expected to come down, and particularly with a lower concentration of tropospheric ozone in the hemispheric background. So then, yeah, that is what I've depicted here. But yeah, of course, yeah, we are sure that it's very difficult to achieve this. Particularly, yeah, we need first to achieve the methane emission reduction, and only when it is successful, that reduction may come.
Thank you. Charles, did you get it? Oh, you're here.
Yeah, thank you for thank you for the reply. But I would like to say maybe we can have further discussion about this issue. But I think during the reporting on the reporting there, I think we were not able to see the impact of Ukraine war, and we were not able to see the impact of the increased demand for natural gas. So the reduction in methane is now a very, very big challenge to the world. Yeah, that's my comment.
Yeah.
Anyway, thank you.
I totally agree. Yeah, the methane reduction also promised last year with a global methane pledge with a 30% reduction within 10 years. Japan also signed, but yeah, of course, yeah, with the new things, particularly with a new war or something like that, yeah, may make it even more challenging. Thanks.
Thank you. So we do have one more question in the chat box from Chuck Chang. Chuck, are you online? If you wish, you could speak up, or I can read for you.
Oh, thank you. So I was just trying to ask that the speaker mentioned about EC emissions could be 10 times more in the future from forest fire. I'd like to know what would happen to the organic carbon emissions from forest fire. Any projections in the future? Yeah, thank you.
Yes, thank you very much for the important question. I'm not very much familiar with the output of that ESM. That is from the German ESM. So then, and that paper was also focusing just on black carbon. But we may easily guess that the organic carbon emission will rise similarly together with the black carbon. So then, as long as they are flown in the atmosphere, maybe the net effect might be low. But for the boreal forest fires concerning the deposition of the aerosols, only the black carbon amount increase is to be concerned. So that was my point here. Yeah.
Okay. Thank you.
Okay, thank you. So I think we are just like time to conclude. Is that correct? And then we have some, I don't know, 10 minutes break before the next speaker. Or you have a control, or how can I do from here?
Any questions from our side?
Oh, we can take more questions. Yes, that's good.
Yeah, I'm a bit worried about the larger temperature rise for the Arctic region. So, what should the people in the world do to reduce this, or what happens if the temperature rise really happen for the Arctic region? It seems it's higher than average. And what should we do? What the people on Earth should do to prevent this?
Yeah, that's quite important question, and I'm not the right person to respond to this very big question. But you're right that people living there are very much affected by the very rapid change maybe in sometimes the East Siberia region, the temperature rise is so huge, and melting in the ground of the ground is a quite important issue that they may lose their houses and in the unstable ground, something like that. So then, yes, and another point is that there would be a feedback from that change in the Arctic to the global. So then, of course, when the sea ice area is reduced, they were pretty much reflecting back the sunlight to the space, but that function is to be lost. Then the global effect is that kind of feedback becomes much more significant, and that feedback may also go through the forest fire intensified as well. So then all the system needs to be thought about, and the scientists may what scientists can do is to reduce the uncertainty of the prediction into the future, and to which time of day some mitigation or the adaptation needs to be made, something like that. And of course, the Arctic Council and the AIMAP are serious about this. So then, people are getting the information from the Earth integrated models, and then trying to get the right information out of this to deliver that information to the public or the stakeholders or relevant people. Sorry, my point is a bit vague, but that would be the right way to go, I guess.
Okay, thank you. That's quite helpful. So
thank you.
Few minutes.
Oh, we have yes, we have one more question in chat box from Shalwi Wu. Can you speak up if you want?
Sure. Thanks. Dr. Kanaya, thanks for your talk. I just want to know that because I realized that there are quite a lot of papers looking at brown carbon absorption from the literature about both the wildfire emissions or just urban emissions. And some of them have found that they could be as important as those emitted from the urban anthropogenic activities, can be as important as BC. So just wondering, do you foresee in the near future that IPCC will include that portion to improve the accuracy of the model? Thank you.
Yeah, thank you very much for the important question. And the inclusion of brown carbon to the IPCC report is a bit stagnating, I would say. It was mentioned in AR5 day, but no much information is included in the current AR6. And the two papers that was included in the AR6 and was in my slide was the only major achievement during this 7 or 8 years. So then, of course, a part of the organic carbon is treated as a totally cooling agent in the current climate systems, typically in the climate model simulation, particularly participating in the CMIP6 intercomparisons. But if the part of organic carbon is affecting the warming side, that maybe the view is totally changed. It is to be changed. So then the quantification of the brown carbon, the amount in the atmosphere and where it is coming and how it changes is a great challenge for us, for the atmospheric chemists to tackle in the coming years. And Asia is pretty much nicely located to study this, I would say. And the model simulation that I've exemplified today, Jan et al., the paper 2020, is saying from the model simulation that maybe they are coming from 3 major sectors, from the biomass burning, biofuel burning, and secondary atmospheric chemistry, and including nitrogen species of the aromatic species, something like that. So then the processes need to be more carefully studied, and how much they are produced and how they are lost from the atmosphere and how they are breached, for example. Some literature says that the OH radical reaction with those BRC, brown carbon, may reduce the color or something like that. So then the bleaching effect may be also important too there. So then all the processes need to be studied carefully. And yeah, of course, of field measurement, remote sensing, or the some color measurement of the aerosols, or those to be collected, or those to be done and in a systematic way. And yeah, we are hoping to form some society to get all the data together to be ready for the next reporting setup.
Okay, thank you. Thanks.
Okay, thank you very much for many questions and discussion. Nice discussion. So maybe shall we wrap up?